It was also, by the way, it was fun to see Valerie Rapson's name. I'll take a little shine in reflected glory time to let you know that Valerie was actually my PhD student here at RIT, and she did a sterling job on her PhD. So it's wonderful to see her flourishing out there in the professional world. Okay, so I'm going to walk you through the James Webb Space Telescope from the standpoint of two standpoints I've written here. One is the standpoint of the image chain. And since you're in the Carlson Center for Imaging Science, I get to kind of bludgeon that idea home a little bit. It's a useful way of looking at how images are obtained in all different contexts, scientific contexts. And it's particularly useful, I think, when you go to look at astronomical imaging systems of all kinds. And I think it's particularly useful to think about as complicated facility as the James Webb Space Telescope from that standpoint. And then hopefully I'll have time to give you my selfish take on what James Webb Space Telescope will be really fun to use to look at astronomical objects. So, and obviously, shout out in the chat or raise your hand in the room here if I'm glossing over something you might want to know a little bit more about. So this is, by the way, something that I also beat my students over the head with. I'm actually doing this right now in a class called Fundamentals of Astronomical Imaging, which is a general education course here at RIT. All different majors from across the campus take the course. The idea of the imaging chain. So there's all kinds of ways to look at the way images go from source of energy, source of radiation, to the final image that you appreciate with your eyes and brain. These 7 or 8 steps, depending on how you break them down, are a really nice way to look at that. You've got some source of radiant energy. You could be looking at a star cluster. You could be looking at a nebula. That's a source of radiant energy, electromagnetic radiation. Of course, this whole chain, by the way, doesn't have to be restricted to electromagnetic radiation, but that's all I'll be talking about tonight. We have colleagues, Michael and I do, Stacy and I do, here at RIT that study other forms of energy in an imaging sense, gravitational waves, for example. I'm not going to talk about that. I'll be talking about electromagnetic radiation. So you have a source of energy. It's emitting light at some wavelength. You have an object that you're interested in imaging. Now, typically in astronomy, those two things might be the same thing. A star cluster, for example, is emitting its own energy. The moon is not emitting in the visible wavelength range. So if you want to image the moon, then you're imaging an object that is not the source of radiation. So it's nice to break those things apart so that you can analyze them separately. Then you've got collection. Collection means optics, lenses, mirrors. Detection, that means sensors, arrays, sensor arrays typically in modern astronomy now. Processing, which is usually intimately tied to the sensor. It's almost impossible these days to separate the processing from the sensor that's actually grabbing the light. Transmission. Once you have an image, you're going to want to move it somewhere else. So you have to transmit the image typically. Storage. You've probably stored the image already even before you've gotten to the point of transmitting it. So you have to, so often these 3 steps at the end here have to be interrelated and moved around. So after that comes the science, after the storage step. You can display the image if you so choose. Often in astronomy, we just need to grab a whole bunch of images and not necessarily look at all of them. We want to process them somehow and then look at the end result of that processing. You're going to perceive the image in some way, shape, or form. That's one of the whole ideas of imaging. But for science applications, you may not even get to the point of displaying the image before you do data reduction. I kind of mentioned that a second ago. You'll be processing the image in some form, working with the image. You'll be doing some sort of analysis on the image, typically. How bright is this star that I've just measured? You'll want to know how many counts did this star produce in my sensor relative to some other star, perhaps? And then you're going to interpret that in some way that's going to get you science at the end. So this is the way that I like to look at it. And those of us here in the Center for Imaging Science, we have very different disciplines, and we need to talk to each other about how images are taken and manipulated. And this is a handy way that we can talk to each other about that without having to know a lot about what our particular disciplines are. So let me put, I'll come back to the image chain in a sec. Let me put the James Webb Space Telescope in context. These are 3 of NASA's great observatories. There's a 4th one that's not on here, which is the Compton Gamma Ray Observatory. Ah, yeah, Michael was about to say that, right? I don't know why. So I have to say a couple of these slides I got from the James Webb Space Telescope project. And I don't know why they decided to take the Compton Gamma Ray Observatory off of this particular slide, but whatever, that's their business, and we don't have to worry about that too much right now. This is a sequence, I guess, in order of not in order of launch, but in order of missions that are still around, having been launched. Spitzer is an infrared telescope. It's still out there, but it's been turned off for the time being. I can talk about that later if you like. It's interesting. Chandra is the mission that I worked on back at MIT for about 6 years or so pre-launch. Got to RIT in 1999, literally the week before Chandra was launched in July of 1999. So I became a user of Chandra after having been the one of the people who worked on the software from the science perspective for Chandra. So I went from developing software to being one of the people that yells at the people who are developing software that they didn't do things right. Often I'm just kind of yelling at myself when I look at that, the data that I get from Chandra. And then there's the Hubble Space Telescope, which has been operating now for over 30 years. Quite amazing that it's still a frontline astrophysics facility, but it definitely is. As far as where the James Webb Space Telescope sits with respect to those other, at least 2 of the 3 other space observatories I just showed you, big NASA space observatories. This is a schematic of the electromagnetic spectrum, showing that the Hubble Space Telescope is mostly concentrating on the visible part of the electromagnetic spectrum. It also has coverage into the ultraviolet. It's actually, I think, right now the only functioning telescope up there that can actually do ultraviolet imaging and ultraviolet spectroscopy. You need to be above the atmosphere to get ultraviolet radiation, to collect ultraviolet radiation and analyze it. So Hubble is playing a huge role there still, and will until it stops functioning, which hopefully won't be for another while. And then on the other side of James Webb Space Telescope is the Spitzer Space Telescope, which operated from what we call the mid-infrared out to the far infrared. And you can see the Webb Telescope, the Webb Space Telescope, sort of occupies the electromagnetic radiation domain in between the 2 of them. It's very much an infrared-centric observatory. I'm wondering if Michael's going to point out that, or Stacy, that the wavelength ranges you see here, which are in nanometers, you should not use capital N and capital M. Again, this is another slide. I'm passing the buck here. This is a slide that I got from the project, so I'll have to yell at them at some point about their use of the incorrect nomenclature for units there. Our visible wavelength regime, the wavelengths that our eye can see, run from about 3,800 nanometers out to almost 7,000 nanometers. I'm sorry, I'm talking angstroms. Thank you. Boy, it's a good thing we got people checking me out here. Yeah, 350 nanometers, excuse me, to 700 nanometers. Thank you. And you can see that that James Webb is capable of seeing just a bit into the visible wavelength range, 600 nanometers. But it goes way out to 28,000, almost 29,000 nanometers. And at that point, those numbers are so big, we would prefer to put them in microns. That's about 30 microns, 29 microns or so. So now having sort of moved to microns, this is just a quick table showing you the wavelength domains of various observatories, most of them space-based, that have worked in the infrared regime. The first one that really was a workhorse facility was the Infrared Astronomy Satellite, IRAS. And it had rather poor spatial resolution, ability to see fine detail in the sky, but it covered a wavelength range that had really not been covered before with any amount of detail and with any amount of comprehensive coverage of the sky. So IRAS covered the entire sky between wavelengths of 10 and 100 microns and really opened up the infrared regime. And I won't go through all of these missions, but you can see that they complement each other in terms of their wavelength coverage. They overlap in some respects, and some of them cover areas uniquely. One of them is a ground-based facility, the 2-micron all-sky survey. And those of us who are interested in stars and galaxies and studying those objects rely on the 2-micron all-sky survey in all kinds of different ways, because it covers the entire sky at these wavelengths that are just beyond, just above, larger than the eye can see. So you come down the list here and you notice that the James Webb Space Telescope is now the only one of these that's operating. So there's a very heavy onus placed on this space observatory, and it's in many respects much more powerful than its predecessors. But you can see that it's limited to a certain part of the electromagnetic spectrum, about half a micron to 30 microns. Some of these missions covered wavelengths that were longer than that, but none of them covered those wavelengths, as I'll talk about in a bit, with the sort of spatial resolution and sensitivity that James Webb Space Telescope offers us. Sure.
In relation to the part, because black bodies that are hotter than sun, they will emit more short wavelengths. If you do a star which is very far, it will emit short wavelengths.
Yes. So the question is I can repeat if you like. Question for those of you on Zoom is, why are these particular observatories not covering the visible wavelength range where hot stars, or stars like the sun actually, and hotter, are putting out most of their radiation, visible light? Well, that's a great question, but I guess the answer lies in the fact that there's a lot out there in the universe that's a whole lot cooler than stars. For example, the planet that we're sitting on right now, our bodies that we are emitting almost all of our radiation at a wavelength of about 10 microns. So if you want to see planets, for example, around stars, then you're well advised to go to the wavelengths that James Webb Space Telescope is optimized for. Dust in the universe tends to be, excuse me, a lot cooler than the objects that are radiating, so on. So yes, there's an argument to be made for covering the entire electromagnetic spectrum with as much sensitivity and spatial resolution as you can possibly put together. And it's one of the great strengths of Webb that it's focused on the infrared, and it's also a limitation, if you like. And it remind me to mention later on that this James Webb Space Telescope is not the highest resolution, spatial resolution telescope that's operating right now, and that's important to know. It is the highest resolution telescope as far as spatial acuity, fine resolution goes at these wavelengths. Sorry? Chara, yes, right. If you put telescopes together into interferometers, you can do better. Yeah, and I'll talk about if I have time, the radio interferometer that can actually get to higher resolution than the James Webb Space Telescope. So the infrared astronomy imaging chain. So we've talked about, I showed you sort of the schematic imaging chain at the beginning of my talk. If you want to adapt an imaging system to work in the infrared, if that's your goal, to see objects that are cooler than the sun, essentially, then you've got to think about the different pieces of the imaging chain that need to be modified. And the first thing is Earth's atmosphere is essentially opaque to wide stretches of the infrared part of the electromagnetic spectrum because of water vapor, because of methane, because of other molecules in the atmosphere that absorb infrared radiation very effectively, which is what gives us the greenhouse effect. So in order to, excuse me, in order to defeat that, the best way to do it is to get above the atmosphere. It's the only way to do it if you want to see, if you want to get actually access radiation that's in certain parts of the electromagnetic spectrum in the infrared. You have to get above the atmosphere. You have no choice. So that's one thing that you would like to do. You'd like to get above the atmosphere if you can. If you want to collect radiation that's in the infrared, then you've got to be able to actually collect infrared photons of lower energy, photons that have longer wavelengths. So those are aspects that change the way that we might want to think about our reflecting or our refracting surfaces that are collecting the light. We also want to see cool objects in the infrared. And that's really hard if your telescope or your camera or the combination of them is warmer than the object that you're trying to see. That in that case, your camera and your telescope is going to be looking at itself, essentially. It will be radiating, so the infrared radiation you'll see will just be the telescope itself. So you have to really cool the telescope down, and you have to cool the camera way down. And then the detection stage in the imaging chain, silicon, which we all rely on for visible wavelength observing with our CCD devices or our CMOS sensors in our cell phones, for example, silicon doesn't work for wavelengths longer than about 1 micron. Those wavelengths are too long, too low energy. They don't cause electrons to be excited in the silicon so that you can count them. So you need to go to a different sort of material. So I will now try to, from the standpoint of the imaging chain, and I'll probably accelerate the talk a little bit right now, walk through the JWST from the standpoint of how it's been optimized for infrared, for the infrared imaging chain, and also just what an amazing feat of engineering JWST is. And I'm not an engineer, so some of this stuff I don't fully understand, and I will confess that right now in front of you, but I can describe for you the different ways in which it's put together, and we can discuss it. So there's a very nice PBS Nova, by the way, that's dedicated to JWST, and I would encourage you to watch it if you haven't seen it yet. How many people have seen that? Oh, it's really very well done, I think. So it's really well worth seeing. And our colleague, our faculty colleague here, Jehan Kartaltepe, is featured for like 30 seconds or something like that in the Nova. So by the way, Jehan has secured about 200 hours of JWST time during the early so-called early science and then cycle 1 of JWST. She has the largest single general observer program. And when I say she does, it's the team that she's leading of, I don't know how many, several dozen astronomers who study galaxies. So she knows what she's talking about, and she does a nice job explaining it in that. Jehan Kartaltepe. Yeah, you can look her up on our RIT's website. And by the way, if you fall asleep during my talk, because it's already getting late, you can just go to the website that the Webb folks website, that the Webb Telescope has put together, the Webb team at Space Telescope Science Institute. They've done, and Goddard Space Flight Center. They've done a very, very nice job organizing the information that I'm talking about here. Most of the information I'm conveying to you, I went to the website and got it. I am also on the JWST Users Committee, as was mentioned during the introduction, and which means that I'm one of about 12, 15, I forget how many astronomers, most of us from the US, a few from Europe and Canada, who consult with the project and get briefed regularly. And so I'll talk a little bit about a couple of the briefings that, one briefing that I've gotten so far as part of that user committee work. And I'll have another one in about 2 weeks, I think. At the end of the month, we'll go to Baltimore again and watch the project give a dog and pony show and get to ask them questions at that point. I'm sorry, jump forward. Oh, no, let me go here. Okay, so this is a quick view of JWST from kind of an image chain perspective. And I'll be talking about each of these things in turn. The optical telescope element, which is the main collection, if you like, where the light is collected by JWST's mirrors. The science instrument module, which is where the detection, actually more collection goes on, there's more optics in there, but where the detection actually happens, that's where the images are actually captured in the science instrument module. And then the sun shield and spacecraft bus, which are there for the health and safety of the telescope in various ways, and also to keep it cool, the sun shield in particular, to provide that cooling function that I mentioned that's so important for the infrared. This is just a different view of the same elements, and some other things are sort of called out there for you. And I'll be sort of running through each of these in sequence. From the main optical telescope element, its primary mirror, its secondary mirror, the light going back to the instrument module, the ISIN behind the primary mirror, and then the various spacecraft related things that are what JWST uses to communicate with the Earth in both directions, taking commands, executing the commands, and then sending the data back. And then various things that have to do with the powering of the instruments and pointing of the telescope. So one of the most striking things about JWST is the way in which its mirrors are constructed, or its mirror is constructed out of an assembly of hexagonal elements, each of which is about 1 meter in diameter. And you can see this, it's a different approach to building a mirror than, say, the Hubble Space Telescope, which is a monolithic 2.5 meter circular mirror with a hole in the center, because it's a Cassegrain design. The Hubble mirror weighs something like 1 ton, and James Webb's actually a lighter telescope than Hubble because of the way it was designed. And this is sort of a breakaway of the telescope elements. And I show you this just to give you a sense for the complexity and engineering savvy that went into the Webb's mirror assembly. You've got the sort of lattice structure that the mirrors are suspended onto in the back, and then the main mirror collection system of the hexagonal segments, 18 of those segments that match onto the lattices that you see in the back. And then there's this structure that holds the secondary mirror out in front. You can see the secondary mirror assembly sort of blocked out for you. You notice there's no tube, right? The whole thing is just sitting out there with no housing. And that's another thing that's rather striking. It's very different from the Hubble Space Telescope, which is kind of a traditional telescope in the sense that it's sitting in a tube. The Webb telescope is an open to space telescope, and that's intentional. That's because if you have the telescope sitting open like that, it's free to radiate to the universe at large. And the universe has a characteristic temperature of about 3 degrees above absolute zero left over from the Big Bang. So if you can successfully keep the sun from shining on this whole system, then the telescope will simply match, eventually come as close as it can to the temperature of the universe, 3 degrees above absolute zero. It never quite gets down there, but it gets fairly close, as we'll see in a bit. Yeah.
Is that the first telescope that was designed that way with no housing?
That's a great question. I don't know the answer offhand. It's probably not the only space telescope that's been designed that way.
Space telescope.
Yes.
There are plenty of ground-based telescopes built in exactly the same way. If you go to any of the big cellophane or leaf, you'll see people who built telescopes exactly that way.
Right, right. Yeah, yeah. So here's a blow-up view of the individual mirror segments, the 18 mirror segments. Don't ask me why they have the designations they do. I'm sure the engineers had their reasons for calling. You know, it looks like the A's are toward the center, and the C's and B's are out toward the edges. Yeah.
I'm curious if each mirror is the same size or if
They-
they're a little bit different.
They are almost exactly the same size, all 18 of them. Yeah, yeah. As far as I know. So yes, so it is really like having 18 telescopes pointed in the same direction. Each of those mirrors can be individually steered very carefully and can be deformed, I think I'll show you in the next slide. And the idea, of course, is that you want them all functioning together as one unit. But the very first images that Webb took of a star, a reference star, there were 18 images on the detector. And that was a good thing, because that way they understood exactly what the properties of each mirror were now that they had been launched in space. And they were able, they had planned for this, they were able to move the mirrors individually to get those 18 images to overlap perfectly. Yeah, great question. So I think this slide shows you each of the 18 mirrors separately, you know, as they were being configured and coded and so on. And then this is a back view of an individual mirror segment that shows the complexity that's involved in just one of these mirror segments. Instead of being a hunk of glass that's aluminized, as you know, we sort of tend to think of a telescope mirror, these are beryllium hunks that have been emptied of a lot of their mass. You notice there's this kind of hexagonal pattern in the back, triangular, bunch of triangles. So it's a beryllium sheet, if you like, but a lot of the beryllium has actually been removed. And I've forgotten now just how thin they are, but it's of order millimeters thick, the beryllium substrate that the mirror coating is placed on. And the mirror coating is gold. I think if you add up all the gold that's been used for the 18 mirror segments, it's not a lot of gold. It's not enough to go to the bank with, because the mirror coatings are so beautifully thin, and that's also to keep the weight down, obviously. And you can see the control that the engineers have engineered into each of these segments. They can be deformed in very clever ways and very sensitively deformed so that you get the perfect mirror figure to focus light. I'm going to skip over the video here. There's a nice video that you could take a look at that's on the website that shows the path of the light through the system, off the main mirror, off the primary mirror, off the secondary mirror, back through the hole, because there's 18 mirror segments. There's a hole right in the center of the mirror, essentially, and that's where the light comes into the science instruments area. And so that's what I'll switch to now, moving from the collection part of the imaging chain to the detection part of the imaging chain, where the sensors are. So this is the science instrument module region of the telescope. It sits back here, the colored parts in this schematic diagram. The instruments are housed right behind the main mirror where the light path brings the image. And they are powered and controlled by electronics. It sort of sits underneath inside the spacecraft. And if you want to kind of visualize, a nice slide that allows you to sort of visualize how the instruments, there are 4 main instruments on JWST, how they are configured on the sky. This is the focal plane, if you like, of James Webb Space Telescope. And in the little insets here, I'll use the cursor if I can, you can see the wavelength coverage of these different instruments. I hope. Let's see, it's hard for me to see from here, but this says near infrared and this says mid infrared. The near infrared going out to about 5 microns in wavelength. So that's about 10 times longer than the middle of our visible wavelength range, out to a wavelength of about 30 microns. The Miri instrument is the mid-infrared imager and spectrometer instrument, covers the mid-infrared part, and then the near-infrared is covered by 3 different instruments, the fine guidance sensor and near-infrared imaging slitless spectrometer, and the near-infrared camera, NIRCam, and the near-infrared spectrometer. So there are actually 2 different instruments that can take near-infrared spectra, and I think the nearest can also take images. And the NIRCam is sort of the workhorse infrared camera that covers the near-infrared, and then Miri is the mid-infrared camera and also does spectroscopy. And as I mentioned, silicon doesn't work for detecting visible light. So the material scientists have to find materials that have sensitivity to longer wavelength, lower energy radiation. And that forces us to go to things like mercad-tel, mercury cadmium telluride, and arsenic doped silicon. So this is silicon with a fair amount of arsenic in there, which allows the longer wavelength radiation to actually generate electrons inside that material. And mercad-tel has been used actually for a long time from the ground for ground-based infrared observations. And the Webb engineers managed to build some very nice large format sensors that can access, they can use that material that can access it. So these are slides showing what these sensor arrays look like if you see them close up. This is the NIRCam sensor that's made of mercad-tel. And I believe each of these is about a megapixel, something like that. And as is this Miri sensor, that's the arsenic doped silicon. You can see, get a sense for the size of these things. One of the nice things about the way the Webb sensor and processing systems have been designed is that you can actually access the image as the exposure is proceeding. And that's really a great thing if you want to avoid saturation in the sensor. Often when you're observing in the infrared, you're looking at something for the first time. No one's actually accessed that wavelength before for that particular object. So there's some chance that you're going to get things wrong when you go to figure out how long you want to expose your, how long you want your exposure time to be. So it's a nice feature of the instrument that you can actually grab the image at various times as the signal is building up. And then I just included this this slide because I think it shows the amazing complexity that's involved in just one of these instruments. This is the Miri instrument, the mid-infrared instrument. Even in its imaging mode, you can see how many reflecting surfaces are involved in getting the light from the telescope focal plane onto the sensor, onto the detector. Here's the filter wheel, and this diagram right here shows you the different wavelengths that each of the filters can access for the mid-infrared instrument. You can see it has coverage mostly in sort of medium to broadband filters, all the way from 5 microns out to 30 microns. And so you can select each of those pieces of the electromagnetic spectrum through the mid-infrared using the filter wheel here. If you like, you can use a more complex mode of the system. And my brain explodes when I look at the schematic diagram for the spectrometer. So in order to take a spectrum, to break the light into its component wavelengths from 5 to 30 microns or so, at a resolution of about 3,000. So you're breaking that part of the spectrum up into 3,000 chunks. In order to do that, you actually have to take a sequence of about 8 spectra, and it's possible to set up the commands for the Miri instrument to do this. And the light will go through a sequence of filters and a sequence of and be reflected off a sequence of gratings in order to give you the full range of the spectrum from 5 to 30 microns. In order to do that, you can see how many light paths have to be followed here. It's rather amazing. So that's we've made it back to the sensor part of things. Here's how we actually talk to the spacecraft, that is James Webb Space Telescope. And this schematic shows commands coming from the Space Telescope Science Institute to the ground station for the Deep Space Network. The Deep Space Network is the workhorse here for JWST communication. It's a group of radio antennas that can send very strong signals. So radio signals are sent to Webb. The commands are encoded in those radio signals. Webb receives the radio signals, interprets the commands, sets up the instruments to do the exposures. The data are taken. They are sent back by Webb, by its radio antenna, back to the Deep Space Network. And then that data is transmitted over here, not over here, to the Space Telescope Science Institute. If you're looking carefully, you'll note Baltimore is actually over here. It's not over here. You'd think that they would get that right, but anyway, yeah. Close, it's close. So one of the interesting things, by the way, about the use of the Deep Space Network for Webb, it's actually Webb, between Webb and the Artemis moon mission, the Deep Space Network is now about as stressed as it can possibly be. And so there's a bit of concern that whenever Artemis is going up with people up there, they take priority. Obviously, there are human lives at stake at that point. There's some chance that the Deep Space Network will have to be completely devoted to Artemis for long enough periods of time that the folks at Space Telescope can't actually talk to the James Webb Space Telescope. And if it doesn't get signals from the ground for 24 hours or so, it goes into a form of safe mode, which means it basically sits there waiting and does not take data. So there is a situation possibly going to happen in the future where JWST will be idle. And as for a $10 billion science experiment, you really don't want that to happen. So there's a lot of, I would say, activity involved right now in trying to get the Deep Space Network upgraded to the place where perhaps we won't have to worry about that. Webb's, your question?
I just statement. We've added 2 telescopes in the last 2 years.
Yeah, yeah. Right, right. There's been a lot of chatter now about trying to improve the both add more telescopes and also go to higher frequencies. So yeah, the place I used to work, Haystack Observatory, operates at the K-band that would be the optimum place to do this. And so maybe they'll use Haystack. I don't know. Yeah. So this is just a quick schematic showing the unfolding sequence of first the sun shield, which had to open up, and then the mirror assembly. So basically, Webb had to be disassembled, if you like. It had to be folded up, launched, and then reassembled in space. That this actually worked as according to plan is amazing. I think it still amazes all of us who were worried that the whole thing might not work. And if you want to see more about this, you can go to the Webb website, and you can actually click on each of these different stages in turn, and it'll describe what took place, how it had to happen, and when it happened. A lot of it happened in the first 24 hours or so, as far as the main unfolding. And then another month went by while Webb went out to its orbit, which is about 4 times further away from us than the moon, about 1 million miles away. So all of that, as I just mentioned, went off without a hitch. Unless you count, as we were just talking about earlier today, unless you count the one rogue micrometeoroid hit that the telescope took, the mirror took, I believe it was one of the C elements out near the edge of the mirror. That the project realized that a mirror had been hit by a micrometeoroid because suddenly the image quality degraded measurably. The image quality, by the way, is about 3 times better than they expected it to be. It was 3 times, well, I should say it was 3 times better than it was specified in the requirements to be. It has diffraction, Webb has diffraction limited imaging at 1 micron, and it was only required to have diffraction limited imaging at a wavelength of 2 microns. So its image quality is about twice as good as was required by the science that Webb was designed to do. So it's really working very well. Yes.
If it had that non-open thing, give up something to not being able to close that, but would that protect it a little bit so it would only does Hubble support the same?
No, Hubble doesn't, and maybe for a couple different reasons. It's in low Earth orbit, whereas James Webb Space Telescope is way out there at the second Lagrange point. But yes, so I guess I'll jump ahead to something I was going to mention, which is that when that micrometeoroid hit happened, you can see down here. It says, these are the slides, by the way, we were presented with at the users committee meeting back in August. And I found it this sort of amusing. 6 micrometeoroid events were in family. In other words, they were about as damaging as they expected. The damage was very slight. One of them, the damage was measurable on the mirror. So there was a lot of concern, obviously, if another half dozen or so of those kinds of hits were sustained by the mirrors, then the image quality would degrade to the place where you could actually start to worry about it. It might not be diffraction limited anymore at 2 microns. So the idea now is a simple idea. Instead of being arbitrary about where the telescope is pointing as it orbits the Earth, just turn around and always point in the direction away from the motion of the Earth around the sun. So James Webb Space Telescope is in a solar orbit. It's essentially trapped, trailing the Earth, following the Earth around in its orbit, and it's out there about 4 times further away from the Earth as the moon's orbit. So all you have to do, quote unquote, is turn the whole telescope around most of the time. There'll be exceptions when there are objects that astronomers want to look at that are in the direction of the Earth's motion. But for the most part, that can be avoided. What's that?
It's not geostationary?
It is not geostationary. No, no. Well, it's geostationary in the sense that it's trapped in this orbit where it's being tugged along by the Earth, but it's actually orbiting that point. So it's actually moving around that point in space. So yes, and this is the illustration that I was just concept I was just talking about. So here's the Earth. This I just grabbed this morning. You can go on the website and click on where is Webb, and you can get this very nice interactive map of the solar system and the Earth Moon. So you can zoom in on the Earth Moon system. And it will show you where the Webb Space Telescope is relative to the Earth Moon system. And it's hard to get a sense of the perspective here, but it's the sun is back in this direction on this side of the Earth, and Webb is actually about 4 times further away from the Earth than the moon's orbit. And one of the reasons that it's way out there is that it's incredibly cold. It's got a sun shield that was deployed early on in the mission that blocks the infrared radiation from the sun. So it blocks the visible light and infrared radiation from the sun. Does not hit that radiation does not hit the mirror and the science instruments. And so if you look at the side of the telescope that's facing the sun, it's nice and warm, 55 degrees Fahrenheit. If you look at the side away from on the other side of the sun shield, things are very, very cold, down to tens of degrees above absolute zero. And furthermore, there's a cooler, there's actually a refrigerator that's attached to the mid-infrared instrument that gets it all the way down to 6 degrees above absolute zero. And apparently they stopped tracking this at a certain point, the change in temperature. This is the change of temperature with time since near launch, a few days, well, I guess like 30 days after launch. And you can see the temperatures drop after the sun shield was deployed. And this is the cryo cooler, I believe, for the mid-infrared instrument, the refrigerator turning on. So that the temperature plunged to 6 degrees. And the rest of the instruments are nice and cool, below 50 degrees Kelvin. So that allows that access to the infrared spectrum that I was mentioning before. So this is another slide that we were shown at the users committee meeting back in August. Green means meeting or exceeding spec. And this is one of the most amazing things, you know, the engineering marvel that JWST is reflected here in the fact that almost every indicator, every metric that you could think of, Webb is exceeding the specifications that were set up for it. And it's doing better than it was when they were testing it on the ground. Well, okay, there are a couple things that have gone wrong. There was a problem with the gratings wheel on the mid-infrared instrument back, actually right around the time that we had this users committee meeting. We weren't told about it at the time because the engineers had just discovered there was something going wrong. They didn't know what was going on at the time. It took about 3 months or so to sleuth out the problem. Apparently, if you turn the gratings wheel in one direction, it tends to stick. If you turn it in the other direction, it's fine. So now the gratings wheel on the mid-infrared instrument will always be turned whichever direction that is, clockwise or something like that, and never counterclockwise again. And apparently it's been working fine ever since. So if only all problems were that easy to fix, right? So, yes, sure.
Thanks.
Mhm.
What kind of power requirements does that have to keep it that cold?
I couldn't really tell you other than it's not that much power because it's it's just fine to use the solar array that Webb has to collect the energy for it. So Webb is completely self-sufficient in terms of its power. It's got a solar array, and that's
Do you know how much
providing
the
everything.
sun shield is made out of?
No, I don't. I've forgotten now. Michael, do you remember what the, yeah, I'm not sure what the sun shield is.
Captain. Not Mylar, it's Captain.
What is that?
That's the follow.
Yeah, I'm not, yeah.
But to follow up on the question about the coolant, is there a liquid coolant used for some of the detectors that has a limited lifetime and will boil off?
No, I don't think so. I'm not sure, actually, I'm not sure about the cryo cooler for the mid-infrared instrument. Yeah, but right now, the one limiting thing would be the propellant to point the telescope, and that's the limiting thing, not any coolant that's used for the Miri for keeping Miri cold. The propellant has at least 20 years right now of lifetime. It was only they were only counting on 10, so it's got about double the lifetime right now that the requirements demanded of it. And that was because the launch was so flawless. There was just very little extra maneuvering required on the part of Webb to get it where it needed to go. So it should be fine. Yeah.
There were two things, that's the question, there were two things, just putting batteries on. If it was, I mean, 9 years and extend a wind-up coding for batteries. I mean, you should have something like that. And putting Spitzer, why wasn't there a picture? Why didn't Spitzer have a picture?
I don't know that. I don't know the answer. Yes. Yeah. Well, I mean, right. I guess I agree with you that, it would be nice to have done it some other way so that it lasted longer. But on the other hand, Spitzer did last a lot longer than they were planning on, so at least it outlived its planned lifetime. Yeah. Well, we will lap Spitzer. The Earth will lap Spitzer because it's in the solar orbit, and then maybe we can grab it and refurbish it at that point. Now I guess I'll just spend a few minutes on the selfish science part of this. The Webb Telescope rollout really happened last July, and I think everyone saw the wonderful images that were released on July 12th. The president got to see them on July 11th. One of the exciting things for me personally and my students was that a planetary nebula was included among the subjects of the first Hubble, first James Webb Space Telescope images. And you can see the planetary nebula here featured in this kind of press release view of the very first images being worked on by the Space Telescope Science Institute team that had chosen the first targets for the Webb telescope, and had actually sent up the commands, processed the data, gotten those first images, which all were really jaw-dropping images, every single one of them. So planetary nebulae, perhaps that's for this crowd. I don't have to run through a lot of the background on what a planetary nebula is, but I'll give you a quick rundown. For stars here that are called low mass, and that means sort of a star that's roughly got the mass of the sun, maybe up to 5-7 times the mass of the sun. Those stars will never have the mass in their cores that they're going to implode as supernova. For a star that starts out with about 8 times the mass of the sun or more, those stars, once they exhaust all of their nuclear fuel through fusion, there'll be so much mass left in the core, over 1.5, 1.4 solar masses, that the core will collapse and explode as a supernova. And that's what you see in the bottom sequence down here for a massive star. For a star like the sun, that star, when it uses up its core hydrogen, it's converted it to helium. It'll also then fuse helium into carbon, but it doesn't get further than that. You wind up with a carbon-oxygen white dwarf at the center, and the material that never participated in fusion, which is about half or more of the star's mass, actually expands to become a red giant, and then eventually that red giant is so luminous toward the end of its life that the material actually gets pushed away. And as it gets pushed away from the core of the star is still very hot, has a lot of ultraviolet radiation. That ultraviolet radiation ionizes the former outside layers of the star and causes a beautiful planetary nebula like you see here. This is the Eskimo Nebula, has an NGC number, 2392 or something like that. You wind up eventually with a white dwarf, and the material that was part of the star, the so-called envelope of the star that didn't participate in fusion, that material with some nuclear fused contaminants gets spat back out into the interstellar medium. And that's why we all have carbon and oxygen in our bodies, and there's nitrogen in the atmosphere that we get to breathe and so on. All that stuff was produced very likely in intermediate mass or lower mass stars like the sun. The oxygen, a lot of that gets generated in supernova explosions, or gets generated, I should say, by stars that are on their way to becoming supernova. It's a better way to look at it. But a lot of the carbon and nitrogen especially comes from planetary nebulae, objects that went through a planetary nebula phase. And so you can also look at that, if you like, in terms of the HR diagram. Star like that has, say, twice the sun's mass, starts out here as a main sequence star burning hydrogen in its core, exhausts the hydrogen, starts to burn hydrogen in a shell around the core of the star, becomes a red giant. Eventually, it will get to the place where it starts to fuse helium in its core to carbon. At that point, it kind of becomes a main sequence star for a second time, but it's a helium-burning core helium-burning main sequence star. After all that helium is used up in the core, the star will then start to fuse hydrogen in a shell, and inside that fuse helium in a shell into carbon. And at that point, you get what's called an asymptotic giant branch star. That's the phase just before the planetary nebula. Eventually, the outer layers of that asymptotic giant branch star, which is an enormous structure, probably about the size of the Earth in terms of its diameter, probably something like the Earth's orbit. So that star then will blow away its outer layers. A lot of dust forms inside the envelope of the star that's being ejected away. And the dust is very good at absorbing infrared light. It's almost like little solar sails. It pushes the rest of the material away. And at that point, you start to see inside the hot core of the star, and you've got temperature here running to the left, the way astronomers like to do it on an HR diagram. So the star at that point gets much hotter. And when it gets to the place where it has a lot of ultraviolet radiation, then it becomes a planetary nebula. It's ionizing the material that it's lost. So it's at this point that we start to see a planetary nebula. And these objects, of course, are beautiful. They've been the subject of Hubble Space Telescope imaging over the last 20 years. And what's really striking about planetary nebulae is that although the stars out of which they formed originally were spherical, a lot of planetary nebulae are not spherical. They have interesting shapes. There's obviously a lot of energetic phenomena that are going on that astronomers are still sort of trying to understand. We don't really know exactly how this whole process works. So planetary nebulae are actually very interesting objects if you want to understand, we think, how binary stars end their lives. One of the explanations, one of the theories that might explain why an originally spherical object, when it starts to lose its mass, starts to lose that mass very aspherically, is that it has another source of gravitational potential energy lying around, namely a binary companion. That's a source of both gravity and also orbital angular momentum that can redistribute the material that the star is losing as it becomes a planetary nebula. So we've been working on this problem for a while now in various ways, and in fact, using the Hubble Space Telescope in part to study these objects and try to understand their three-dimensional structures and how much mass is being lost and what the composition of that mass is. And perhaps from analyzing these images, we can get a better idea how the binary companion to the primary star that starts losing mass as a red giant, how that binary companion can shepherd that mass loss. So I was particularly excited when I saw this image from the James Webb Space Telescope, because I had grabbed an image in the infrared from the ground with a 2-meter telescope on Kitt Peak about 30 years ago that we published in a paper where we were interested in looking at the molecular gas that's left over around a planetary nebula. So I've just said that planetary nebula is an ionized gas cloud around a very hot star. That hot star is generating a lot of ultraviolet radiation that is essentially shredding the atoms. It's ripping the electrons off of the positively charged nuclei in the atoms. Apparently, though, there's a lot of molecular gas that's left behind. We think that molecular gas probably is a sign that there's a binary star in the system that's managed to shepherd some of the mass that's lost from the very cool red giant star in specific directions, and maybe allowed it to survive because so much of it is showing up in certain directions. It's basically self-shielding itself. So that was one of the ideas that we've had for a long time. So it's very exciting to see this image, and it's especially to see in gory detail exactly where, and shown in red here, by the way, is the molecular hydrogen. So we can really see exactly how modeled that molecular hydrogen is in appearance, how structured it is. It's showing up as little pockets of molecular gas. That's something that we really didn't see from the ground at all. And we also didn't see, by the way, just how far out this molecular gas is going. So these images from James Webb Space Telescope were quite breathtaking to see. These are on the left are images from the near-infrared camera I was mentioning. So this is the one that covers wavelengths from about 1 micron out to 5 microns. And that includes wavelengths, in particular this 2.12 microns and 4.7 microns, where molecular hydrogen is especially bright. It also covers wavelengths where, for example, ionized gas is very bright. 1.87 microns, that's a wavelength where ionized hydrogen that's recombining, electrons are finding protons. That's a wavelength where you see that process happening. So you see both the ionized gas and you see the molecular gas very clearly. You see the same sort of thing happening here in the mid-infrared, and here the filters are a little bit broader band, so you're getting more wavelengths and therefore more processes captured at each of these particular wavelengths. Yes, thank you. So this is a quarter of a light year. Right. So these objects span a fair distance to the nearest star that would be surrounding this particular object. Right, they're big structures. Yeah.
Is the boundary between the ionized gas and the molecular component as stark as it appears?
So I'm really glad you asked that question, because the question was, is the boundary as stark as it would appear? So I loved this press release, these set of press release images, but I found them a little frustrating as well. So these were early release science images from James Webb Space Telescope. They were public domain. You or I or anyone can go and grab these images from the archive, the James Webb Space Telescope. They're not subject to a proprietary period, as would be the case for a scientist that has proposed to use James Webb Space Telescope and wants to publish something on the basis of those data. These data are freely publicly available, so one can go and grab them. And that's what I did just a couple days after the images were released, because I wanted to answer the very question you asked. Is the ionized gas and the molecular gas distinct, or is it intertwined? What can we learn from that? So what I did was I grabbed the images on the one hand that isolate ionized gas. This is so-called Paschen alpha transition of hydrogen gas. So this is atomic hydrogen that's just recombined. It was recently ionized and it's just recombined, and it's emitting a photon of Paschen alpha, which is the, help me, Michael, is it the 5 to 4 transition or 4 to 3 transition of hydrogen? I've forgotten now. 4 to 3. And bracket alpha, therefore, is the 5 to 4 transition of hydrogen. And then this so that's color coded blue for you here. And the Paschen alpha is color coded blue, I should say. The bracket alpha is color coded green, and color coded red is emission from twice ionized sulfur, S3. Interestingly enough, though, what this really shows us is a companion star that's sitting off to the side of this hot star. It turns out, actually, that the hot star here is not the source of the Planetary Nebula. It's actually this reddish object. And that was a surprise. And what it tells us is that there's a lot of cool material around the mass, the star that's lost all of this mass. There's still a lot of cool dust around it. And that, again, is kind of a smoking gun, if you like, for the presence of a binary companion. It turns out the hotter star that is the one that sort of dominates the light here, that hotter star is kind of an innocent bystander. It's a very widely separated binary companion. And there's probably a closer companion that is sitting right next to the star that's lost all the mass that's generated the Planetary Nebula. We can also see that the ionized gas is relatively smooth. This image on the right is entirely composed of individual images that isolate molecular hydrogen. So this is the ionized gas, and this is the molecular gas. And they have very different characters. And it's I think, showing us what we kind of expected, which is the molecular gas is very mottled, it's clumpy. So it's probably survived in molecular form because it's clumps that are hard to break up with ultraviolet light. It's going to take many more thousands of years for the ultraviolet light from the central star to break up these clumps of denser gas. Yeah.
Joe, the filaments in the right-hand panel that are inside the ring,
Yes.
are those filaments of gas that lie outside the ring physically, but between us and the ring, so we're seeing them in projection?
If only we knew.
Inside the ring.
If only we knew. So my guess is that this is foreground and background molecular gas. We have got observing time coming up with the submillimeter array on Mauna Kea at in the radio wavelengths using carbon monoxide at high spectral resolution, which will allow us to see the motion of that gas, we hope. And then if we can convince ourselves that the same gas that's emitting in carbon monoxide is also emitting in molecular hydrogen, 2 hydrogens bonded together. If we can convince ourselves that that's the same gas, then we can probably say whether or not that material is approaching and receding in front of and behind that central ball of ionized gas or not. I have long looked at these objects, and in my own head, well, I'm getting ahead of myself. I have seen objects that that are actually like the butterfly type nebulae that I showed you earlier, and we're looking at them along the axis of the nebula. I'll show you an example of that in a second. So,
There's another question.
yes, oh, sorry, go ahead, Steve.
The other star, is this the observation that discovered it? And what tells you that this other star is the source of the nebula and not the previously famous one?
Okay, so the answer to your first, so the two questions are, was this other star known before? The answer is yes, it had been detected from the ground, and it was thought to be the source of the planetary nebula. The reason being that this star has all the characteristics, if you take a spectrum of it, it has all the characteristics of a normal hot star, as opposed to a star that just blew itself away. And this feeble little thing here has the right properties to be a white dwarf. What was very surprising about the James Webb Space Telescope image is there's a lot of dust at that very hot star. That dust has probably been orbiting for a while.
And you see the two stars also press release picture of the previous slide.
Yes.
The two stars go together right hand.
Yes, there you go. Right.
And that's what the press release text says, that we've shown that thousands of people at the planetarium say just that. But I'm glad to hear more about it.
Yes. Right.
Can you explain, Ms. Joe, why the left-hand panel does not show the second star, but the right-hand panel does?
Yes, because this is a mid-infrared image, so it is most sensitive to radiation that's characteristic of a temperature of this room, 300 degrees. So what this means is, well, okay, two things. The star that's sitting next to the star that's sitting next to the bright one is so small that it really doesn't emit much visible light. It's actually a lot hotter than the star that is emitting a lot of visible light. But that star that's a lot hotter, I'm sorry, the star that's a lot hotter is a lot smaller. It's about the size of the Earth. It's a white dwarf. It's on its way to becoming a white dwarf. So it's probably not quite the size of the Earth yet, but it's on its way to becoming that. So it's the star that's lost all this material is tiny. It's hot, but it's tiny. And this star that's sitting next to it is a normal hot star. It's putting out a lot of visible and ultraviolet light. Yeah. Did I answer the questions? Okay.
I think you probably alluded to just to make sure. The bright star, it's enveloped in the nebula along with the other stars.
Yes.
Not just like behind it.
That's a great question. Yes. So we know that now on the basis of Gaia data. So the Gaia space astrometry mission has shown us that this star is moving along with its little partner. Yeah. The two are moving along together. Yeah.
Why is this nebula
It's about 800 parsecs. So it's about 2,400, 2,500 light years away.
that we are seeing now actually happened?
Yes. Yes, it's right. We're seeing it as it was 2,500 years ago. And based on the expansion speed of this nebula, it's about 3,000, 4,000 years old. So it actually would look quite different now. It would be about twice the size on the sky. And by the way, if we've now, there are images from the Hubble Space Telescope that were taken about 20 years ago. So now we have James Webb Space Telescope images. We can actually see the expansion. It's a tiny effect, but you can actually watch this thing expanding.
Where is the geoprobe?
Where's the what?
The geoprobe.
Yeah.
Oh, Gaia. Gaia is also out at orbiting the second Lagrange point. It's out. It's also following the Earth. Yeah, it's not going to hit the James Webb Space Telescope. It's like gnats in the Grand Canyon. right? So they're not going to collide or anything, but it's been placed in the same basic orbit as James Webb Space Telescope, the Gaia mission. Yeah. Were there other questions? Sorry. Yeah, so let's see. So not long after we put this together, this montage, a bunch of us decided this was an opportunity to show the astronomical community, the astrophysical community, the power of the James Webb Space Telescope where planetary nebula studies were concerned. So my colleague Ursula DeMarco is largely to blame or to credit for putting together this large group of us and shepherding the cats in the wheelbarrow, as it were, to get us to converge on a story that we think that these images are telling us about a multiple star system. Has to have at least 3 stars. The bright one that we that you can see in the image so clearly in the shorter wavelengths. The fainter one that shows up is the hot star that's also got cool dust around it, and probably at least one companion very close by to that hot star that's still got dust around it. And I'm very proud of the fact here that we have not just me, but 5 RIT co-authors on this paper. 2 of whom are former students of mine, Jesse Bublitz and Rudy Montes, and one is a present student here at RIT in the astrophysics program, Paula Moraga. And Jason Norhaus, who's our colleague, faculty colleague, also contributed to this paper. And the Space Telescope Science Institute folks did a much better job combining those images that I had originally combined, and they worked their magic and produced this set of images for the press release that went out coincidental with the release of the paper. And we actually made the cover of Nature Astronomy. They couldn't resist how pretty these planetary nebulae are, I guess. So quickly, here's the Butterfly Nebula again. It's got an NGC number. We know now, right? This is the new general catalog. So this object's been known for a long time. It's been cataloged for a long time. But with every set of images that's taken, we learn more about its structure. And we published a paper based on Hubble imaging earlier last year, about a year ago now. These were images that we collected with Hubble in 2019 and 2020, using its wide field camera, which was the last instrument that was installed on Hubble. It's the best camera that's available on Hubble, and it's got a huge number of filters. And we just a group of us that I led just said, what would we see if we threw everything that the wide field camera on Hubble has at this beautiful nebula, this Butterfly Nebula that had been imaged many, many times before, actually by Hubble. And we picked some filters that people hadn't picked before. For example, this pink that you see here, that's the light of iron in the near infrared, showing up in the near infrared. There's actually some overlap in the wavelength coverage of Hubble Space Telescope and James Webb Space Telescope. They can both facilities can cover this region around 1.5 microns. So we're hoping we're going to get another image of this object with JWST in the same line, same emission line. But what was fun for us is when we saw this image, we realized we were seeing something completely new about this nebula. You only see this particular emission line of iron when you have a very energetic outflow phenomenon, a collision happening between 2 gases. So what we think we're seeing here is gas that was ejected by the red giant star that is now being shaped. It's being hit by a very narrow collimated jet that's coming from the central star of the nebula. That's probably the only viable explanation for why you would see this particular emission line of iron. It requires a velocity, a collision velocity of about 100 kilometers per second to light up that particular emission line. So what we're probably seeing is a wind of about 100 kilometers per second that's hitting this nebula. So it's a beautiful nebula. It's shown us all kinds of things over the years. And then you can ask the question, what do these 2 nebulae have in common? we've sort of started to talk about it. Well, maybe we're looking, when we look at this nebula, the one that Webb has imaged now, the Southern Ring Nebula, maybe we're looking at something like the butterfly along its polar axis. So I will quickly walk you through a new tool that we're using to analyze this very kind of, or to interrogate that very kind of hypothesis, which is the Atacama Large Millimeter Array. That's a radio telescope array that's at 16,000 feet in the Atacama Desert in the Andes in Chile. It consists of you can use up to 62 radio telescopes. You can point those telescopes all at the same object at the same time. And you are essentially synthesizing a much larger radio telescope. The individual telescopes can be spread over tens of kilometers across this plateau at 16,000 feet in the Andes. When you do that, you can get images at radio wavelengths that are at or can exceed actually the resolution of the Hubble Space Telescope or the James Webb Space Telescope. And so we're getting close to that sort of resolution when we look at this butterfly nebula, NGC 6302, in the light of carbon monoxide and hydrogen cyanide and HCO+. We're seeing a very different structure, obviously, when we look at the emission from the molecular gas than we're seeing when we look at the emission from the ionized gas. And we think what we're seeing is this equatorial plane region of the nebula where a lot of molecular gas has been trapped. It's moving outward, but it's moving outward quite slowly relative to the polar lobes that you see. And it's fairly cold and it's staying in molecular form. With the Atacama Large Millimeter Array, you not only get images like this, you can get spectra at very high frequency resolution. As I was mentioning before, you can see velocity structures that are relatively low velocity relative to some of the other structures that we're seeing in this nebula. And in fact, you can take an image like this. This is in red here is the carbon monoxide. And you can analyze the frequencies that you're seeing in that carbon monoxide, and you can analyze them in terms of red shifts and blue shifts, Doppler shifts. You can take these data and slice them in velocity and look at that velocity slice. Here's material that's coming toward us, and here's material that's moving away from us relative to the velocity of the entire nebula. And what you see is a ring-like shape. So in fact, I don't know about you, but when I look at the ring-like shape at the center of the butterfly nebula in velocity space, I see something that kind of resembles the structure that we see here in the Southern Ring Nebula. It's a ring of molecular gas, essentially, with some structure outside of it that is probably the lobes, the larger polar lobe structures that are coming toward us and away from us. So I'm definitely out of time here, and I'm just going to leave you with these two images sort of juxtaposed, and we're hoping that we can do a swap here and get JWST images of the butterfly nebula, which will show us the molecular hydrogen gas that undoubtedly is sitting distributed inside this nebula, maybe is following the pattern that we see in the carbon monoxide that we can detect with the Atacama Large Millimeter Array. And on the other hand, we would love to get an ALMA image eventually of this nebula so we can see the motions of the gas. We're going to get the data from the submillimeter array soon, I hope. That will be at 5 arcsecond resolution, which is, it's going to look very fuzzy relative to what you see in the James Webb Space Telescope image, but it might still be enough for us to be able to see the motions of the gas and figure out what's going on. So I've talked for way too long, and you asked me some great questions. I'm happy to keep answering questions, but I'll stop there for now. Thank you.
Any isotopes of beryllium?
Do we see isotopes? So yes, that's another very interesting thing about the especially about the ALMA data. We have sufficient frequency resolution that you can tell the difference, for example, between 12 carbon CO and 13 carbon CO, or hydrogen cyanide with carbon 12 and hydrogen cyanide with carbon 13. So we're going to actually be able to analyze those data and understand the isotope ratio of, or be able to measure the isotope ratio of 12 carbon to 13 carbon, which, by the way, is a fundamental test of the process of helium fusion that should go on in these stars. Yeah. Michael.
Joe, I'd like to do a little, with your permission, a little crowd citizen science thing.
Oh, I'd love to. Yes, do it.
This is the last slide there that shows butterfly nebula.
This one?
Yep, yep. So I'd like everyone who's sitting here, and people who are at home as well, to silently, you have to do this silently, very important, to look at the picture of the butterfly nebula and just think to yourself, is it perfectly sideways? You're looking at it perfectly sideways, or is one side pointing a little bit towards us and the other side pointing a little bit away? So just think about that for a moment. Okay, and if you, so now I want people to we're going to have a vote on, do people think that the left-hand side is coming towards us, or the right-hand side is coming towards us? So on the count of 3, you have to raise your hand. If you're on the Zoom, you can raise your hand, raise hand. If you think the left hand is coming towards us, on the count of 3, raise your hand, otherwise keep your hand down.
And I will not vote.
2, 3.
Okay.
And now, if you think the right-hand side is coming towards us, now you should raise your hand on the count. 1, 2,
Interesting.
3. Joe, I think there's some kinematic evidence that tells us which side is pointing towards us. Can you tell us about that?
There is indeed.
Tell us which.
So, okay, those of you who voted for left, let me make sure I understand my left and my right. Those of you who voted for left coming toward us are correct. Yeah, and so that has been known actually for this nebula for quite some time, because telescopes on the ground have been used with a so-called long slit spectrometer. You can take a slit and put it across this nebula sideways. It's fortuitously organized on the sky for us, almost oriented perfectly east-west. This image is north up and east to the left. So it's almost perfectly east-west. You can put a spectrometer slit across this nebula, and you can look at an emission line and look at the Doppler shift. And you can see that it's blue shifted toward the left and it's red shifted toward the right very clearly. That's the simple story. The more complicated story is it's also moving toward and away from us sideways. The lobe is actually inflating like a balloon that has popped probably recently. Each of these lobes on either side. So if you look at it in detail, it's a lot more complicated than what we just said. And if you really look at this object, you can see many, many lines of symmetry running through it. I think you'll agree. It has beautiful point symmetry, this object. And it is not alone. I have put in a JWST proposal at cycle 2 to look at 8 of these guys, this one and another 7, that all seem to show this point symmetry. And what we're hoping we're going to see is this iron emission that is there in most of them and is saying, aha, now I am spewing material out like this. I used to be spewing material out like this. And before that, I was spewing it out like this. So this is telling us there's probably a processing ejection process that's going on. That's already getting into the land of, we need at least 2 companion stars. You're probably aware that the Earth's axis is precessing, and that's because it's got the moon on one side and it's got the sun as well, right? I think. Do you just need, or do you just need the moon to do that? I think
The moon,
all you need is the moon.
it helps that second.
Yeah, anyway, okay, I won't go venture into lands that I don't belong. But anyway, in order to explain this kind of a phenomenon, you probably need a tertiary system. You need 3 stars in order to get this precession happening. One companion isn't good enough.
I see 2 axes, maybe with a long
Yes.
this way, and then you're saying that it heightened jets that. is
Yes.
An angle, is that?
We're quite certain that the active outflowing gas is going out in this direction right now. These blobs you see here are moving out much more slowly. They were probably ejected a long time ago, and they're moving out very slowly. And they are moving in a different direction completely. They were ejected about the same time, and they're moving out more slowly.
What about timeline? If it's would they be kind of cooked? Why is it?
Yes.
Is it long lived? Is it long lived? You just long lived.
I think you're right. It is sort of a corkscrew.
I don't see it. You see it.
Well,
One request coming
this
from Zoom,
image
could
actually
you
is
use the
only a
microphone?
small
for
piece of what's a
questions?
larger nebula, and there's a big blob that's sitting way out here and way out here too. So it does look like over time it's been ejecting material in different directions at different speeds.
Could we possibly
Well,
use the
it's
microphone?
much
for any
harder
questions?
to see small scale rotation like that in these individual blobs. Yeah. I don't think we could detect that. You can detect the large scale axial motion.
How can a way to work this iron?
So great question. So that iron is probably there from previous generations of stars. It was incorporated into the material that has been ejected. It was part of the red giant before the red giant underwent fusion.
The iron.
Yes.
Yeah, we see iron arsenic enough to that extent.
Well, again, it's showing us a particularly energetic region of the nebula. It's been heated up to the place where you can see that iron in that state. And that's why we're fairly certain that it has this high velocity associated with it. Otherwise, you wouldn't see iron in that particular state. The iron is, yes, it's a great question. So the iron is threaded throughout this nebula, probably at approximately the same abundance everywhere, but you're only seeing it where it's being whacked. Does that make sense?
That makes sense. That was awesome.
Yes.
In the right middle wing of the butterfly,
Right middle.
you have kind of a folded look.
This,
Do we know what's going on there?
well, my guess is you're seeing the ultraviolet eating away at that fairly dense material, ionizing it over time. These, there's my colleague Bruce Ballack is working on these same data. He's been analyzing Hubble Space Telescope images of this object that date back 30 years now. And you can watch the different regions of this nebula expanding at different velocities, and you can pin down specific ages when these various ejections happen. It's this corkscrew we were talking about, and it does seem to be point symmetric. The first one was like 3,000 years ago or something like that, and the most recent one is this iron, the pink that you're seeing here, and that's about 1,000 years old. So whatever this object is doing, it appears to be doing it repeatedly and in different directions. And the easiest explanation, is that you have some sort of a processing jet system.
Jackie, are there any questions from the chat?
No questions. I do have a couple of comments. There was a question about what. the
I wish I could hear you better.
Oh, well, let me try this. that better?
So,
Ah.
Kathy answered what the.
Okay.
Yes.
Answered what captain was.
Right,
So,
captain.
So the sun shields are
Sun
made of
shield,
captain.
Layers of
Thank
material
you.
called captain. Each layer is coated with aluminum. When the sun facing side of the two hottest layers, designated layer 1 and 2, have a doped silicon or treated silicon coating to reflect the sun's heat back.
Nice. Okay. Thank you.
You're welcome. I looked it up.
And Marty referred to as
Yeah.
radio astronomers.
Right.
And if there are any other questions from the auditorium, if we could use the handheld mic for us poor people on Zoom, that'd be awesome.
Yes. Yes. Thanks. And I meant to, just asking for the handheld mic wherever the questions come up. I meant to relay them. I haven't been doing a good job of that. Well, I really appreciate everyone's attention through what I think was maybe an overly convoluted and complex talk, but I appreciate the attention.
Maybe another 2 years?
Yeah, sounds good. Happy to do that.
That is going